The problem in the image is a classic second-order linear ordinary differential equation, ODE. Frac d2x dt2 plus k frac dx dt equals 0, subject to the initial conditions x of 0 equals 0, quad frac dx dt, right t equals 0 equals v0. It asks us to show that the solution is xt equals frac v0k, left 1 minus e minus kt, right, breaking down the problem. This equation represents a damped motion without an external driving force. The term frac d2x frac dt squared represents acceleration, while k frac dt is a velocity-dependent damping term. The constant k0 is the damping coefficient, determining how quickly the motion slows down. The given initial conditions mean that the object starts at the origin, x equals 0, but has an initial velocity v0. This is a physically common scenario. For example, releasing a moving object into a resistive medium, such as a body sliding on a surface with friction proportional to velocity, or a small sphere moving in a viscous fluid. Why this question is significant. 1. Foundational in dynamics and control systems. This ODE is one of the simplest models showing how energy is dissipated in real systems. It's directly linked to first-order decay behavior and is foundational in modeling physical, electrical, and thermal systems. 2. Connection between transient and steady-state behavior. The solution contains two terms: a transient term, ET, that fades over time, a steady-state displacement, frac v0k, reached as t2 inf d. This distinction is vital in engineering because it shows how systems settle after an initial disturbance. 3. Broad applicability. Similar forms arise in RC circuits, heat transfer, population growth decay, and chemical kinetics. Once you master this equation, you unlock a tool for solving problems across disciplines. 4. Gateway to advanced topics. Understanding this derivation builds confidence to tackle more complex ODEs involving oscillations, nonlinear effects, and forced responses. Why learners should be excited. This problem is more than an exercise. It's a bridge between mathematical theory and engineering reality. It shows how a simple equation predicts a system's complete motion over time, how damping influences behavior, and why initial conditions matter. Mastering it equips students with a tool they'll use repeatedly in fluid mechanics, vibration analysis, electrical engineering, and beyond. It's the kind of problem that turns abstract calculus into real-world predictive power.